All right, so chemistry. What is chemistry? Chemistry, by definition, it's the study of matter. All right? And by the way, if I write something on the board, then it's generally important, especially if I put a little star next to it, right? So I would definitely recommend taking notes, take a picture if you want to. That's fine as well. But I would take notes and so that you can review that when you're studying for the test. So chemistry is the study of matter. That may not be that helpful. That's really not that helpful unless we understand what matter is, right? So we have to also define matter when we define chemistry. And so matter is anything that has mass and takes up space. So that's how we're going to define matter, which is what we're studying in chemistry. Anything that has mass and takes up space. So what that means is that almost everything that we see would fit into that definition, right? The one thing right now that we're seeing in this room, and maybe you could argue, well, I'm not really seeing it, I'm seeing the effect of it. I don't know how you would define that. But one thing that's present right now that would not be classified as matter is light. Okay? But almost everything that we see, and there's a lot that we don't see. For example, the air around us, right? That's still considered to be matter because it does in fact have mass and it takes up space. And I think the lab that we're doing next week is basically proving that, right? So anything that has mass and takes up space would be classified as matter. And like I said, that's almost everything that we see would fit that definition. And so the reason I'm stressing that, and like I said, even the air falls in that category, even some of the things that we don't see fall into that category, is here's my greatest burden with chemistry as I'm teaching you guys chemistry. I love the subject, I love to teach it, but the thing about chemistry is that chemistry was invented by God, right? It was created by God. And so if I'm going to study chemistry, then that's also going to be a study of the one that invented chemistry. So my biggest goal here is always to point you guys to Christ, right? And this is what I want to read Psalm 19, 1 through 3. It says, "The heavens declare the glory of God, and the firmament shows his handiwork. Day unto day utters speech, night unto night reveals knowledge. There is no speech nor language where their voice is not heard." And so what that passage says right there is that the creation is screaming at us that there's a God, right? It's screaming at us in a language that no one can deny. The things that you see, I had my 6-year-old nephew here with me last week, and I put a pile of Legos in the middle of the floor. And we had just built, I think it was a jet or something, we built like a little jet next to it. And I put a pile of Legos there, and I said, "Mason, what do you think? You think if we wait for 5 minutes, if we just leave that pile there, that after 5 minutes there'll be something constructed and built from that?" And it's like, he's 6, No. Well, maybe if we wait for 3 hours, right, those pile of Legos will slide together and start forming something, and maybe there'll be a skyscraper there made from those Legos. No, he probably told me that was stupid. It sounds like something he would say, right? Nobody believes that if we left a pile of Legos there that they would just make something amazing, right? And yet that's what we swallow down when we say that there's not a creator, right? We're looking at this grand creation around us. We're looking at the amazing level of diversity, right, and detail and creativity that's displayed in the creation. And the Bible says it's screaming at us that something this amazing, there has to be a God, right? There has to be someone that created this, someone that made this. And so that's the point when you're studying matter. You're studying all of these things that we see around us. And all of these things that we see around us are screaming at us that there's a God. Romans 1 says that it's declaring to us his eternal power and Godhead so that we're really without excuse. There's nobody that can truly deny that there's a God because the creation around us is screaming that in a language that everybody understands. All right, so when we study chemistry, we're really studying the work of God, and so we're seeing Him, and it's designed to glorify Him. So as much as I can bring us back to that, I want to bring us back there. Okay. So anyway, talking about matter, it's anything that has mass and anything that takes up space. So when we talk about mass, when we talk about something take up space, we're going to be asking questions like how much space does it take up, right? How much mass does it have? And in order to do that, we're going to have to measure it. So we need to start talking about measuring these things and what's involved with doing these measurements. As we're performing the labs, measurements are going to be very important, right? So we need to know how to work with the measurements. And so I want to talk a little bit about measuring things, and we'll start with length, measuring length. But we need to define something called a unit. And a unit is a quantity that describes the measurement being made. Being made. All right, and I think everybody here knows what a unit is, but maybe you've never thought about how would you actually define that. But what are some of the units that we use for measuring length? What's a unit? If I measured how long this table width would measure it in feet, right? So feet would be a unit of measurement associated with length. If I was measuring this marker, right, I might use inches. Maybe I'd use centimeters, maybe millimeters, right? We know a bunch of different units of length. So a unit's just a quantity that describes the measurement being made. When we say something's so many feet long, that makes a different picture in our mind than saying that something's so many inches long, right? So it's kind of a frame of reference, a quantity that describes that measurement is made. And units are extremely important. So this is what I want to make sure that you guys do whenever you're doing your problems. Always include units in your answers, right? If it's a problem with a unit in the problem, always include the units. It's critical that we do that because, like I said, if something's 12 feet long and I just write down 12 and you assume it's 12 centimeters long, we're on a completely different page there, right? They say that NASA lost a spacecraft that was designed to explore Mars because there were calculations that were done and they didn't write down the units. And one group of scientists thought it was in one unit. I think it was English versus metric units, right? And so that's what messed up the calculations because they didn't include the units. So always include your units when you're writing down your measurements. All right? So when we talk about taking measurements, we need to consider another topic. And any questions so far? No? All right, we need to talk about another topic which is called precision. And let's see, what's the best? Let me first right now draw a little bit of a ruler here. So that was a terrible straight line. This board moves on you while you're trying to draw it. So let's see, 1, 2. All right. So let's say this is 0, this is 1 inch, right? So we're looking at a ruler. Rulers you can usually measure with a couple of different units, right? One side has got inches on it, and if you measured on the other edge, you can measure with centimeters or millimeters. So it has what we call English units on one side, which is inches, and then the metric units on the other side, which are the millimeters and the centimeters. Well, what I want you to get in the practice of doing is anytime we're using an instrument to measure something in this class, it may be a ruler, it may be a graduated cylinder, anything that's got those little lines on it, these little tick marks here, where you can define where you can take a particular measurement. I want you to always try to take your measurements, estimate between where the tick marks are, right? So for example, if you're using a ruler and you're measuring something in inches, there's a tick mark every 1/16 of an inch, right? If we broke that down, we would see that there were 16 equal divisions there between from 0 to 1 inch, right? And so every line on that ruler represents a 1/16 of an inch. This is 1/16 of an inch. This is 2/16 or 1/8 of an inch. This is 3/16. This is 4/16 of an inch, which is 1/4 of an inch, right? And so 1/16 is the smallest measurement that you can take if you're only using the tick marks that are on there. I want you to estimate in between those tick marks. What that means is that with a ruler like this, I want you to use a precision of 1/32 of an inch, okay? Because that's what, if I were to draw little lines here, little dotted lines in between each of these, it would divide up from 0 to 1 inch, it would divide it up into 32 equal spaces, right? And so you should be able to, so the first line here would be 1/32 of an inch. This would be 2/32 of an inch, which is 1/16 of an inch. So the goal is to always measure in between where the tick marks are, okay? Let's look at it on the centimeter side. Centimeters, they're a little easier to deal with. So we got 1 here, we got 2 here, 0 here, centimeters. And it's divided up into 10 equal parts. And so this line here corresponds to 0.1 centimeters. This one's 0.2 centimeters. And so what that means, if I'm using this scale, right, if I'm using this side of the ruler, is I want to take my measurements and measure in between here, right? Which actually would be, instead of, so the first thing there would be 0.05 centimeters, right? And then this area right here is kind of hard to see, but that would be 1.5 centimeters. And so if we were measuring something, in the example that the only thing that popped in my head in the first class, yes, you have a question? No, okay, it was just your pencil. The first class, all I could think of was an English pea. Does everybody know what an English pea is? Those little round green peas. They're disgusting. Does anybody in here like English peas? Would you just be like, I want a big bowl of English peas, and you just, no? Good. Okay, we're all on the same page. What?
I'm really glad nobody raised their hand.
I mean, I think I literally threw up, or almost threw up, when I was made to eat those. I can remember being at like this. It was called Kitty Corral. It's like this little place, preschool place that I would go to, and they made me eat English peas, and I'm pretty sure I threw them up. They were disgusting. So I don't know how big an English pea is, but let's just draw an English pea on here, all right? As best I can. And we're going to say that I draw this English pea, and let me make him a little more round. Comes out to there. And so if I'm measuring the diameter of this English pea, right, it falls right here in between these two lines. And so, measuring this in centimeters, this is 0.1 centimeters, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. I don't want you to say that the diameter of the English pea is 0.8 centimeters. I want you to estimate between. So what your answer would be when you measured the diameter of the English pea is, you would say it's 0.85 centimeters, because that's directly between the 0.8 and the 0.9. Okay? And so always measure, try to estimate between whatever the smallest tick marks are on your measuring device. If it goes to 0.1 centimeters, I'm expecting to see 2 decimal places there, right? If it didn't have these, so that everything was just 1 centimeter, then I would only expect 1 decimal place. All right, but since this one is 0.1 centimeters is what every tick mark represents, then it should be 2 decimal places. All right. Any questions about that? Does that make sense when I talk about precision? And I'll tell you why that's important in a minute, because basically if we write down our answers, our measurements to the right precision, then I'm going to know, based on the number that you wrote down, I'm going to know how precise the measuring instrument is that you used. Okay, so that's why it's important that we write these measurements down with the correct precision. All right. So I'll just write down this comment here. This is kind of important. The reason precision is important is because a precise measurement tells the person the scale of your measuring device. All right? That's why we need to be precise in our measurements, because it will tell the person the scale of the measuring device that we used.
What if it falls like directly on one of the ticks?
That's a great question. And so we need to still report it in a way that it tells them the scale of the measuring device, but her question is this: what if it came directly down to this line, and so the measurement was actually 0.8 centimeters? How would I write that in such a way that it told someone the precision of my instrument? And the key to that is going to be significant figures, which we're going to talk about in just a minute. So that's a great question. But basically the quick answer to that is you would write it down like that.
Okay.
You put a 0 at the end, and because the 0's there, I know that it's precise to that decimal place. I know that there's a tick mark every 0.1 centimeters. Good question. Tell me your name again. I just drew a blank.
Lily.
Lily. Okay. So that's right there's how you get extra credit in class, guys. It's just that easy. Is it Lilly?
Lili.
Lilli. Okay, gotcha. All right. So any other questions about that? Yes.
Could you get it in like perfectly in such a way where it could be like 0.83 centimeters, for example, or does it have to go by fives?
Well, no. Sometimes, depending on the measuring device, we might say 0.83 because it just looks like it's a little closer to that. But the main point is that you would never say it was 0.825. You would never write that down because our device that would insinuate that our device is accurate to that measurement, right? Yes.
So we should always round to 2 decimal spots with that.
For this particular instrument, yes. If you're doing it in centimeters, right? If we were doing it in millimeters, it's a whole different ballgame, right? Because each of these ticks are 1 millimeter. And so if it was millimeters, then I would round to the first decimal place, right? 1 decimal place. But here, if it was 0.825 is what we thought it was, we would round that to 0.83 because we want to be clear by the number we write down what the precision of our instrument is. Okay. All right. All good questions. I don't always write down your name, so you got to keep trying. All right. You got to give me a little more. Lily was the one to kind of break the silence to start with, so she was rewarded with the first name on the board. Nice job, Lily. Okay, so let's talk about, those are great questions though, and actually your question is exactly what we're going to talk about next. So that's significant figures. And significant figures, we have to use those when we list our measurements so that so it's clear what the precision of our instrument is. So significant figure, by definition, significant figure. A significant figure is a digit in a measurement that contributes to the precision. All right? And so here are the rules for determining whether or not a number is a significant figure, right? Or a digit in a number is a significant figure. Number one, it is non-zero. In other words, it's a number, 1 through 9. Any digit that's not a 0 is considered a significant figure. All right, or number 2, it's a 0. And by the way, anytime I write down a z, I'm going to put a line through it so that you can tell that that's not a 2. Okay, so if you see that with the line through it, I'm just writing down a z. It's a 0 between, and I'll abbreviate between with b slash n, between 2, and I'm going to abbreviate significant figures as sig figs, all right? A lot of abbreviation here, just got a lot of material to get through, so abbreviations are our friends. So it's a non-zero number, then it would be a significant figure. It's a 0 between 2 significant figures, that would make it a significant figure. Or number 3, it's a 0 at the end of a number. And this is important. There's an and on this one. It's a 0 at the end of the number and to the right of the decimal. All right, so it only counts if it's at the end of a number. As far as being a significant figure goes, it only counts if it's both at the end of a number and it's to the right of the decimal place. All right, so let's look at some examples and see if you can pick out the number of significant figures. And there's actually some examples in the book here on page number 5. We'll do that. (102.0). How many significant figures? 2?
Oh,
Right, she's rethinking it.
maybe not.
Maybe not, maybe not. Don't look at the answer in the book. I just want to see if you guys can figure it out. Who says, I'll tell you what, 2, 3, and 4. Who says 2? Who says 3? Who says 4? All right, it's kind of, I had a few more 4s than I had anything else, and the 4s would be correct. All right, rule number 1 tells us that both of these are significant figures, right? Because it's a number that's 1 through 9. So those are going to always be significant figures. This 0 here, because it's in between 2 significant figures, by rule number 2, it's also a significant figure, right? This 0 here, because it's at the end of a number and it's to the right of our decimal point, and that makes it a significant figure as well. So this one here has 4 significant figures, all right? What about this one? 0.0405. Anybody want to take a gander at that? Centimeters. How many? Yes?
Would that just be 3 then?
Be 3. So he's saying 3.
I say 4.
You say 4? We have 4. Anybody have another answer? All right. 3s. You're right. Nathan's right. All right, Nathan. Hook you up. It is AN at the end, right?
Well, yes, sir.
Okay. Why 3? Well, again, rule number 1 tells us that those are both significant figures. Rule number 2 tells us that that's a significant figure because it's between 2 significant figures. Rule number 3 only applies to zeros that are at the very end of the number. So if I had a 0 out here, that would be a significant figure. But none of those other zeros can be because they're not between other significant figures and they're not zeros at the end of the number to the right of the decimal. Does that make sense? Okay? That's definitely tricky, but that's why we're going through these examples here. All right, last of all, 12,000 inches. How many significant figures?
2.
Only 2. Elizabeth is right. Because these zeros, even though we have a 0 at the end of the number, it is not to the right of the decimal place, right? Very good. Let me throw another one up there. 34.0050. There we go. How many do you think?
That would just be 4, right?
4 5. I'm up to 5.
4.
Do I hear more? Do I hear higher? 4, going 4, huh? 5, 6. I hear 6. Any 6, 7, any 7s? Did I see a 7? Nobody's saying 7?
7?
Who said 7? You said 7. Didn't you just say 6 or something like that?
I only counted.
How many numbers do we have here? 1, 2, 3, 4, 5, 6, 7. 7's right. Since the Elizabeth recanted. 7's right. All right. And I did that one because I wanted you to be confused by it, because I want you to understand why that's the case. All right? So let's break it down just a second. You don't have to do these rules in order. Right? You can skip. 3, 4, 5, we know those are significant by rule number 1. We know this 0 is significant because it's at the end of the number and it's to the right of the decimal place. Well, by default, if this number here and this number here are both significant, every number in between it is also significant as well. Right? So all of these other zeros are considered to be between other significant figures. So they're counted as significant. All right? So it doesn't matter how many zeros you have in between. There could have been 20 here, right? And every one of those zeros would have been significant. There could have been 20 right here. But as long as there's a significant figure at the end there, it's between other significant figures, right? So it would also be significant. Does that make sense to everybody? Okay? So make sure you remember those 3 rules. This will be on the quiz next week, right? So make sure you understand how to identify the number of significant figures in a number. Okay, let's move on to, we've already talked about how significant figures tell us the precision of a measuring device, but I just want to make sure you understand that. If I say something is 18.00 centimeters long, then what is the measurement of each of the tick marks on my ruler? Not 0.5, it would be 0.1. Right, so here's my ruler, and it would be 0.1, 0.2, 0.3. There's a 0.5 in there, but it's just basically telling me that it's precise to the digit that's just before whatever the last digit is. Okay? So if I had written it as 18.000, then that would have told me that these tick marks were actually 0.01. 0.02, 0.03, 0.04. Okay? Because it would be precise to that number. All right? Questions about that? Make sense? Like I said, we have that extra number on there because we're always trying to estimate in between, right? These areas in between. Remember, whenever you estimate, though, you always, well, we're going to talk about that in a second, so never mind, scratch that. I'll rewind that. I'll erase that from the video. All right. When we talk about precision, something else that we need to discuss is we need to discuss accuracy. All right? So we've just discussed precision. Precision has to do with your measuring device, right? A very precise measurement is due to the fact that you have a very precise measuring device, right? But there's a difference between having a very precise measurement and having a very accurate measurement, okay? So for example, I have a stick. My stick's 5 feet long, right? And I give you a measurement for that stick, and I say that stick is 3.1842200 feet long. And I look at that and I'm like, dude, that is a very precise measurement, right? The measuring device you're using to measure that stick has got to be very precise, right? In fact, it's telling me that this particular measuring device has tick marks at every 0.0001 feet, right? But even though that's a very precise measurement, it's not very accurate, right? You're like 2 feet off in your measurement. So accuracy has to do with how close the measurement is to the true value of the measurement, right? If we know that this stick is exactly 5 feet long, then even though this is very precise, and this is less precise, this would be a more accurate measurement, right? Because it's much closer to the 5 feet. So accuracy has to do with how close a measurement is to the true value. So make sure that we understand that definition as well. Accuracy indicates how close a measurement is to the true value. I don't have my phone none of the time. All right. Make sense to everybody? Yeah. So the more correct a measurement is, the more accurate it is. A measurement could be precise, but not be accurate. And this is my point. When we're taking measurements for labs, what our goal is to be precise. In other words, we're using the instrument to measure whatever value we're trying to get. We're using an instrument that's precise, the best instrument for that job, right? If I want to measure an English P, right, I'm not going to use a yardstick for that. That's not the most precise instrument. I'm going to get something that's got a much smaller scale on it, right? So we're going to try to be as precise as we can with our measurements while also being as accurate as we can with our measurements, all right? Okay, let's talk about one more thing. When you multiply and divide measurements. When adding, subtracting, your answer should be the same precision as the least precise number. So this is what I want to stick with you. When adding, subtracting, precision is what you care about. All right? This is important. You're going to have problems on the quiz about this. All right? When adding, subtracting, your answer should be the same precision as the least precise number. When multiplying, dividing, care about precision with multiplying and dividing, you care about significant figure. You care about precision with adding and subtracting, you care about significant figures when you multiply and divide. Okay? So when multiplying and dividing, your answer should be the same number of sig figs, significant figures, as the number with the fewest sig figs. And just like I did between the B/N, I do with as W/ sometimes. So I think those are my weird, like Z, I'll do like that. If you ever see that, that's how I write my zeros, so you can distinguish my zeros from O's, which is important here when you're doing like oxygen, and you just need to be able to tell the difference between those two. And then usually I'll do B/N for between, and I'll do W/ for with, and I'm assuming you guys are, that's and. All right. Okay, so let's do some examples. So adding, subtracting, you care about precision. Multiplying, dividing, you care about significant figures. All right, so let's see how that actually works out in some real problems. Precision. With precision, I just erased the rules for determining significant figures. So we know how when we talk about the number of significant figures, what we're talking about. When we're talking about precision, we're basically talking about that's as the least precise number, fewest decimal places. That's what we're talking about when we say precision. We're talking about the number of decimal places. All right. So let's do example 1.2 on page 6 in your book. Does everybody have a book, by the way? I mean, if you don't have it today, do you have a book at home? Anybody? I had a couple of people that were still waiting for their books to come in. So everybody. All right, cool. I had made a PDF of this first reading section, so I was going to send it to you if you didn't have it. Example 1.2, what is the proper answer when a measurement of 15.423 centimeters, 15.423 centimeters, minus, is subtracted from 102 centimeters, so I actually need to come back over here, 102 centimeters minus 15.423 centimeters, all right? So we punch that in our calculator, and you're allowed to use calculators in here. You are not allowed to use your phone as your calculator, so make sure you bring an actual calculator to class, okay? You're going to need that next week for your quiz. So scientific calculator is fine. Some of these problems are easier to do. It's just makes more sense punching it in if you have a graphing calculator, but you're not required to have a graphing calculator for this class. We're not doing any graphing. So if I punch that in my calculator, I'm going to come up with a number, this number here. But that's not going to be my answer because I'm adding and subtracting measurements, and I need to make sure that my answer is the same precision as the least precise number as far as the numbers go in the original problem, right? So this problem here, which number is the least precise, the 102 or the 15.423?
The 102.
102, right? There's no decimal there, nothing after the decimal place. So basically, we're going to have to round this number, right, to just the first part here. And how would I round that? What would my answer be? 87, right? So there's a 5 here. So if you haven't done the rounding in a while, right? If the number that's after the number that you're rounding is 5 or higher, you want to round this number up. If it's below 5, if it's 0 to 4, then you would round down. So we rounded up to 87 centimeters. All right, that's our final answer. Yes?
Whenever we come up with answers, should we be less precise in this situation and just round it up?
Say that again now?
For like all answers that we do, should we we should keep it less precise and just round them up?
You should, well, if you're adding subtracting. If you're adding subtracting, you always do the least precise, right? The next problem we're doing is going to be a multiplication or a division problem, and for those, you don't care about precision, you care about significant figures. Okay? All right. So let's go ahead and do the next one then. Is that clear to everybody? How I did that? All right. With significant figures, with multiplication and division, you use significant figures to determine your answer. So in this problem here, this is example 1.3. We have a measurement of, it's the same numbers, 15.423 centimeters, but this time we're dividing that number by 102 centimeters. So now like I said, this is a division problem. And if it's a multiplication or a division problem, we don't care about precision, we care about significant figures. So we're looking for the number that has the least number of significant figures, which is which number? Of these two? Huh? 102. How many does it have? It has 3, right? All 3 of these numbers are significant figures. So when we punch this in our calculator, we get a really long value of 0.1512058823353, right? But because we divided here, we know that we need to round this to have the same number of significant figures as our number with the least significant figures in our original problem. So in that case here, what it means is that we want to round to 3 decimal places, right? And so our final answer will be 0.151. Is that clear to everybody? And we just double check it real quick. This has 3 significant figures. This one does as well, right? So we're good. I don't know if I gave you guys, if we looked at a number like this, I think we did. How many significant figures does that problem have? Does that number have?
5.
No.
Oh.
That was why I wrote it on the board, because that's a confusing one, right? It doesn't have 5 because remember, a 0 is only significant if it's at the end of the number and to the right of the decimal place, right? These numbers here could only be significant if there was another significant figure somewhere out here. Now, if I put a 1 in front of that, then all of those numbers would be significant. But there's no other number in this problem that's significant that's to the left of the 1 there, okay? All right, but you gave it a shot. So tell me how to say your name again.
Arina.
And spell it for me.
Arianell.
Ari,
Aria, and then, like a melody, and then now.
Aria, now. Aria, now. Aria, now. I'm sorry. I'm trying. I need to record myself saying that. I'll practice it 3 times before I go to bed each night. All right, then I'll have it finally. All right, no questions about that? You guys got it? All right. Adding, subtracting, you're worried about precision. Multiplying, dividing, you're worried about significant figures. That will be on the quiz next week, so make sure you got that. All right. Last thing I need to talk about, very important. In fact, man, this if you get this next concept down, your life is going to be so much easier the rest of this class. Okay, because even though it may not seem like it initially, we are doing what I'm about to show you. We're going to be doing this all year long. It's never going away. So if you're confused right now, you need to work more problems and make sure that you get it down. Okay? Let's see what time it is. All right, cool. We're doing much better than we were in the last class. And that is unit conversion. All right, how many in here took the placement test? How many had to take that? Most of you did, right? And so you'll remember when you took the placement test, there were no, I didn't give you any chemical formulas. Right? There was you didn't see H2O on there anywhere, right? No atoms or molecules or anything like that. The placement test was all about math. And that's because there's so much math in chemistry. It's not hard math, but there's a lot of math in chemistry. And there was basically three concepts I was testing you on with that placement test. Number 1, can you do unit conversion? What we're just about to talk about. And like I said, that is so important because you're going to be doing unit conversion the entire course. If you get that down, it's just going to make everything easier for you, okay? And if you start recognizing these problems as basically unit conversion problems, it's going to make your life so much easier. But unit conversion, scientific notation was something that we tested, that I quizzed you on that placement test, and we're going to talk about that next week. And then the last thing was just basic algebra, like being able to rearrange a basic algebraic equation. If I say A equals BC, and I tell you to solve for C. C's a little harder, right? If I tell you to solve for C, you should be able to tell me that C is equal to B over A. Because I multiplied both sides by C, I got rid of that C there. This became CA equals B, then I divided both sides by A. C equals B over A. Basic algebra. If you can do this, and you can do the unit conversion that we're about to go through, you're 80% of the way there of learning the rest of the material, right? We're just doing this type of stuff over and over and over again. So let's talk about unit conversions. In unit conversions, I need to kind of talk about what I did right here, and you need to make sure that you remember that. So you learned something called the factor label method, and if you don't remember that name, don't feel bad. I didn't remember that it was called that either. I just remembered it was something I learned in math and did over and over and over again, right? But we learned that you could do something like this. You could take 2 fractions, multiply them times one another, and what we learned is that if I have a number on the bottom of this fraction that's the same as a number on the top of that fraction, that they cancel one another out. And so the answer to that problem is 7/13. Is that mind-blowing to anybody, or has everybody seen that before? You should have seen it, right? You should have encountered that at some point. If this blows your mind, you need to go look that up, right? And remember how to do that. With Algebra 1, you should have done problems like ABC over DEF, right, times, and they didn't look quite like this, but times DAF over CIJ, I don't know. right? And because there's a D on the bottom here, it cancels out with that D there. The F cancels out with that F there. C cancels out with that C there. And so you have an answer of A squared B over EIJ, right? Something weird like that. You did problems like that in algebra where you were canceling stuff out all the time. So if you're multiplying two fractions together, you can cancel stuff out on the top and the bottom if they're the same. That's the way unit conversions work. I mean, if you got that basic concept down, then you can do unit conversions all day. Okay? Any questions about that basic concept before I move on? This is like your little chance, right, for review with this if something's confusing to you. I don't mind doing some other examples. Okay. So, when we talk about unit conversions, we have what we call a conversion relationship. All right, we may have a conversion relationship where we're relating an English unit to a metric unit. And just to refresh your memory on that, you know, like an English unit that we might use for distance would be feet, right? And the equivalent, and the metric unit that we might use instead would be meters. Or maybe we would use inches in English units and we would use centimeters in metric units, right? I can't remember if I've already said, but in chemistry we're generally going to stick with the metric units. That's almost always what we use, right? But I mean, you also have things like, you know, pounds versus grams. Time is kind of the one place that they decided to say we agree, and so they both use seconds usually for time, right? But for almost all of the other things, whether you're measuring mass or you're measuring distance, you're measuring volume, those types of things, there'll be a metric unit that you typically use for it and a corresponding English unit. Well, with these a conversion relationship says, like, for example, 1 inch equals 2.54 centimeters. Okay? And I wouldn't expect you to memorize that, but I should be able to give you that on a test. In fact, that was one of the problems on the placement test. And if I gave you something in inches, you should be able to convert it to centimeters, right? We don't use this one that often because, like I said, we're typically sticking with the metric system. But something that we use all the time are these relationships. 100 centimeters equals how many meters? Somebody said 1, right? Very quietly. Who said it?
I did.
You? You? Okay, you did. All right. You've said a couple of things. Are you Jerry? Okay, all right. I spelled it right? The cool way. All right. 1 centimeter equals 1 meter. What about 1,000 millimeters? How many meters does that equal?
1 centimeter?
How many meters?
1 meter.
1 meter, right? What about 1 kilometer? How many meters is that? 1,000, right? 1,000 kilometers. So we know all of these conversion relationships. And by the way, these are the three, as far as the metric system goes, these are the three prefixes that I also want you to know. There's a chart on page, there's a chart on page 12 that's entitled Metric Prefixes and Their Meanings. And the three that are bolded there, kilo, centa, and milli. Kilo, centa, and milli. I want you guys to make sure that you know the relationships between the base unit and each of those prefixes. Yes?
How does 1 kilometer equal 1,000 kilometers?
It doesn't. It equals 1,000 meters. So why did you write kilometers on there? All right, you're confusing students when you do things like that. So let's try not to let that happen again. All right. Thank you. Good catch. I've already given you some credit, or I've totally given you credit for calling the teacher out on that. What's so funny is the last class I reversed that and I wrote 1,000 kilometers equals 1 meter.
I wasn't trying to call you out. I really
No, I need that. But it's just hilarious because I wrote it, like I said, I wrote 1,000 kilometers equals 1 meter in the last class, and the girl that corrected me was sitting right there. So that's like that's the seat where that's coming from. All right. So yeah, thank you. That's the way that's written. Always point that out because I don't want anybody to get confused, right? But these are conversion relationships that you should have already seen before. You should be familiar with. You should know that kilo, is 1,000, so that's why 1 kilometer equals 1,000 meters. So you think of 1,000 whenever you see this. You think of 0.01 when you see this. You think of 0.001 when you see this, and that's because we could write 100 centimeters equals 1 meter, but some people remember it like this. They remember that 1 centimeter equals 0.01 meters, right? And you could also write this as 1 millimeter equals 0.001 meters. I'm obviously a guy that gets easily confused, right, as we just pointed out, and so I typically like to do it to stay away from the decimals and write it out like that, right? That's the easiest way for me to remember. But whatever's easiest for you is fine, right? If you prefer the decimal version of this, that's fine. The point is, those are all conversion relationships, so these values are equivalent to one another. And so if I were to write, if I was just using variables and I said A equals B, and then I said A over B, what would A over B be equal to? 1, right? Because this is the same as A over A, and anything over itself is just 1, right? And so that means that we could take any of these conversion relationships here, and if I said 1 inch over 2.54 centimeters, that equals 1, because those are equal to one another, right? And so I could take this value here, this measurement over this measurement, and I could multiply it times anything, and it wouldn't change the value of anything that I multiplied it times, because anything times 1 is always the same thing, right? It doesn't change the value. And so that's really the key that's the key behind doing unit conversions, is recognizing that, all right? So let me give you an example. Let's say I want you to convert 34 centimeters to meters. Well, if you did that, what you would do is you would go immediately to this conversion relationship, right? And you would say, I'm going to multiply that, and this could, if it helps you, this could be thought as being over a 1. This is an understood 1. If it helps you to see this as a fraction instead of just a single number. But I want to get rid of the centimeters, right? And so if I want to get rid of the centimeters, what I want to do is I want centimeters to be on the bottom over here. Because we saw when we were looking at the factor label method a minute ago, that if you've got something on the top of one fraction and something on the bottom of another fraction, you multiply those together, they'll cancel out. And we're trying to get rid of centimeters. So you put the centimeter on the bottom, the unit that you want to end up with, you put it on the top. We're trying to figure out how many meters this is, and so we put meters on the top. And the conversion relationship is that for every 1 meter, you've got 100 centimeters. Okay? And so now our centimeters cancel out, and what we would punch in our calculator would be 34 divided by 100. And when I punch that in, it's going to give me 0.34 meters. Does that make sense to everybody? You should have done this before, but I know how it is. Sometimes you learn something before and you just haven't done it in a while, and it's kind of fresh and new to you. But this is critical, and I cannot stress how important this is, how much you're going to use this concept over and over and over again in this class. It's going to be more complicated than just that, but you've got to get this basic concept down to be able to do the more complicated things.
So, do we need to memorize those conversions?
You need to know these prefixes. And so if you know those prefixes, you should know those conversions. And so those prefixes tell you if you have a base unit, and in this case here, the meter is the base unit. It tells you the relationship of the base unit to any unit that has one of these prefixes on the front of it. Okay? So you should, if this was a gram instead of a meter, you should know how many grams are in a kilogram, right? You should be able to tell me how many centigrams are in a gram and how many milligrams are in a gram, right? Because you understand these relationships. Well, that's really the beauty of the metric system, right? Is as long as you understand these prefixes here, it's not like, in the English system where feet and inches, it's not, everything here is just easily related because of the prefixes. So that's what's so cool about it. That's why we like to use it. All right, so let me do one more example. I want to do an example from the book, but I want to show you this I'm going to do one more example, kind of made up example. And there was a problem like this on the test, on the placement test if you took it. And so I said something like, I don't know, I said, convert 20 feet to centimeters, right? Let me write down here, 1 foot equals what? How many inches? 12 inches, right? So we don't have anything in our conversion relationship here that says so many feet equals so many centimeters, right? But what we do have is we know how many feet, this many inches equals 1 foot, and this many centimeters equals 1 inch. And so what we can do is we can do this in steps. We would first convert from feet to inches, and then we would convert from inches to centimeters. All right, and so this is the way that we would write that down. We would write down 20 feet times, first we're converting to inches, so we want to put our inches on top and our feet on the bottom, so the feet units will cancel out, right? So we know from that top conversion relationship there that 12 inches is equal to 1 foot, so we write that down, and then that's going to give us an answer in inches, but we want to get rid of the inches and end up with centimeters. So we're going to multiply that. We're going to put inches on the bottom because we want our inches to cancel out, and we want to end up with centimeters. So we know that 2.54 centimeters equals 1 inch. Okay, and so it should, when you write it out like that, you should see that feet cancel out, inches cancel out, and we're left with centimeters right here. So if I punch all that in, did anybody punch in 20 times 12 times 2.54 by any chance?
Yeah,
What was it?
Oh, 609.6.
609.6. Who else was giving me the answer? You concur? Is that right? Okay. All right, 609.6 centimeters. Now this is important as well. When you're using conversion relationships, you don't have to worry about precision or significant figures. You can consider a conversion relationship to be infinitely precise and have an infinite number of significant figures, unless I tell you otherwise. Okay, there will be times that I say this is not precise, and so you're going to have to take precision into account or significant figures into account. But most of the time when you're doing a unit conversion, you don't have to worry about that, right? So we would write down our answer like that. 609.6 centimeters. I will tell you that it helps me, especially when I'm doing a bunch of conversions in one problem. I think it's easier to write it all out like this. I think you make fewer math mistakes that way. But I like to write it like this just because it's cleaner. And so I'll do this. And again, I can see very clearly that my units are canceling out like I want, and I'm ending up with centimeters. Okay? So you'll probably see me as we do more complicated stuff write it down like that. But it's the same as this here. I just think that this is cleaner. Don't you think that that's cleaner to look at? This is a little bit, I think to me it's a little more confusing. Okay, let's do any questions before we do an example in the book, and then I'll let you guys go. All right, our example in the book is 1.5 on page 12. And it says an Olympic pool is 0.05 kilometers in length. 0.05 kilometers. And how long is that in meters? So we're interested in this conversion relationship. So 0.05 kilometers. I want to put kilometers or meters on top.
You're trying
Meters
to
is
get
on top.
Meters. I want meters on top because that's what I want to end up with. I want kilometers to cancel out. So I know that 1,000 meters equals 1 kilometer. I can look at that and clearly see that my units cancel out. And so, what is that, like 50? Is that right? 50 meters. All right, so our answer is 50 meters when you multiply that together. And let's see. I've forgotten to mention this to the last class, but let me just tell you guys this real quick. Is everybody clear on that? Does that make sense? The one other thing that you need to note is that sometimes we will do problems Think of units. I've already said this. Think of units as algebraic variables, right? And so, if you remember, in algebra, I could add together 2 plus 5a, and I could get 7a, right? Likewise, I could add together 2 centimeters plus 5 centimeters, and I could get 7 centimeters. But I cannot add together 2a plus 5b, right? Excuse me. I'm glad I was wearing a boot. I wasn't barefooted just then. That would have really hurt. Likewise, I can't add together 2 centimeters plus 5 inches, right? I'd have to either convert this to inches first or convert this to centimeters first, and then I could add those together. And it's the same way with multiplication and division. 2a plus 3a equals, 2a times 3a equals 6a squared. Likewise, 2 centimeters times 3 centimeters equals 6 centimeters squared, right? But if I had 2a, sometimes you see it in this dot notation, 2a times 3b, my answer would be 6ab. In the same way, if I had 2 inches times 3 centimeters, I'd have to write that, if I didn't convert it first, I'd have to write that as 2 inch centimeters. Okay? So think about units as algebraic variables, and that'll help simplify things for you as well. All right? You guys are dismissed. Have a good one.